Hello. So welcome to the first video of Winter Try. This is a video about logarithms. Logarithms are the next type of function that we're going to be talking about. So it'll be good to pay close attention. In this video, we're going to define what a logarithm is and also give an example of something where it would be useful. Okay. So I have a population problem here, something that we could have asked in the last unit. So we're modeling a population by an exponential function. In this case, y equals 100 times 3 to the x. So as before, that 100 is like our initial value, our c, and the 3 is the base of the exponential function. So kind of an unrealistically simple exponential function, but a good example of this type of problem. So as before, x is going to be time in years in this case, and y will be the population. So I can ask a pretty simple question: how long does it take for this population to reach 1,000? Okay, so here's my attempt to solve this problem. I'm going to do some algebra. So I'm looking for when the population reaches 1,000. So if population is y, then I should set y equal to 1,000 in this equation, and then solve for x. So I'm going to try to do that with algebra. So I set up 1,000, which is y, equals 100 times 3 to the x, just plugging in y equals 1,000 in the previous equation. And now the first step is easy enough. If I want to get x by itself, then I could start by dividing both sides by 100. And I get 10 equals 3 to the x. But now I'm kind of stuck because I need to know what power of 3 equals 10. And that's not one that I can just do by hand, right? So I need help. I kind of know by just taking powers of 3 that if I plug in x equals 2, I get 9, right? Because 3 squared equals 9. And if I plug in x equals 3, I get, well, 3 times 3 times 3, that's 27. Okay, so 10 is somewhere between 9 and 27. So the best that I can do right now is say that it's somewhere between 2 and 3. But I'd like to be able to do better than that, or I'd like to at least be able to use my calculator to do better than that, right? Now here's what I'm on the graph, right? If I graph y equals 3 to the x, I can see that at some point this graph does reach y equals 10, right? And what I'm looking for is the x value that I would plug into this exponential function to get out 10. Okay, so exponential functions, when you plug in an exponent, you get a result. And I need something that goes backwards. If I know the result of an exponential function, what's the exponent that I plugged in that got me that result, right? I kind of need to go backwards right now. And the function that goes backwards is the logarithm. That's what the logarithm does. That's what it's defined to be. Okay, so what's going to save this problem or allow me to solve it is the logarithm. So we need to know what that is. We need a function that goes backwards through an exponential function. Okay, so given the output of an exponential function, what was the input? That's what a logarithm function does. It goes the other way. Okay, so we're going to carefully define this. In this slide, we're going to define it kind of informally, and then we'll see the formal definition in the next slide. All right, so our base of our exponential function in that last problem was 3. So the function that goes the other way is called the base 3 logarithm, or just log base 3 is what I'm usually going to say. And I write that as log base 3. Okay, so this right here is notation for a function, right? It is replacing the f in f of x. And usually, I mean, in the past, we've just given a single letter to refer to a function. And this is kind of the first time we've seen a function that we use more than one letter to write it. I guess we've talked about sine of x before, but we haven't really defined that yet. We've just seen it as an example. Okay, so I call this log base 3, and that is a function. And in other words, something that takes inputs and gives outputs. Crucial to note here that the 3 is not the input to this function. It is what's fixed beforehand. Just as I have to fix a base a to get an exponential function, I have to fix the base to get a logarithm function. All right, so what is log base 3 actually do? I mean, in other words, what is log base 3 of x? And also, I hate to be a little pedantic, but note that in this formulation, there's no parentheses around that x like there normally would be for f of x, right? That's just a standard thing. I actually kind of don't like that convention, but you're going to see it all the time, so I have to use it as well. But you can just imagine that this log base 3, you want to read this as log base 3 of x. Okay, so what is log base 3 of x? Well, it equals the answer to the question, what power of 3 equals x? Okay, in other words, it's, again, asking, like, I'm getting x out of an exponential function, out of 3, with base of 3. I need to know what that exponent was. Okay, so we're gonna represent this function in 2 ways on this slide. First, with a graph, right? So here I'm comparing the graphs of 3 to the x and log base 3 of x. 3 to the x is a graph we've seen before, right? It starts out really close to the x-axis, and then it kind of goes up at a steeper and steeper slope, right? Now, to go the other way, in other words, we're basically taking the inputs and outputs of this function and we're switching them around. So the outputs of the exponential function become the inputs into log, and vice versa, right? That's what it means to go backwards. On the graph, what that means is that we're switching all the x and y values. So for every point on this graph, if we switch the x and y values, we get a point on the graph of log. Okay, for example, one point on this graph is 0, 1 on this graph on the left. That's going to become the point 1, 0. Right? In other words, if I plug 1 into the log base 3, I get out 0. Another point on here is 1, 3. That's going to become the point 3, 1. All right. So there's actually a very visual thing that's happening to this graph when we switch all the x and y values. And we'll talk a little bit about this in class. This happens whenever you take the inverse of a function, and log is just an example of an inverse. All right, so I think it can be helpful to represent this in another way, because again, what's happening is we're switching inputs and outputs. So in this second way of representing this function, I start with a function, again, 3 to the x, and when I input these values over on the left, I get out these values. Okay, and I'm just representing that as an arrow taking the input to the output. If you think way back to Unit 1, it's like that machine where I plug something in and I get out something, right? So this is what the exponential function is doing. Now, the problem with this representation is, like, there's infinitely many things I could input, so I can't list all of them out, but I've listed a few of them out here. So what we do when we take the inverse to get the log function is we're switching those inputs and outputs. So what was the output before is becoming the input. Now when I plug in 1/9 into the log base 3 function, then I get out -2. Okay. When I plug in 1/3, I get out -1, and so on, right? So we're seeing 2 different representations, and I think this second representation makes it kind of clearer what's happening almost a little bit. Like they're both of these are getting at that inverse idea that we're switching the inputs and outputs. Okay, so now let's see that formal definition and actually compute some examples of this. So there wasn't anything special about 3 as our base. That was just our example from the problem. We can do this for any base. All right, so when we define log base A, or the base A logarithm, here's the way that works formally. So when I plug in x into log base a, I get out y. And that means, switching this around, that a to the y equals x. Okay, so look at what's happening between these two expressions, and you can see that the x and the y are, again, switching places, right? So when I plug something into the log function and get an output, that's the same thing as if I plug the output into the exponential function, I get back the input. So the way that you can compute log, at least in some simple cases where it's possible to compute by hand, is by turning an equation with a log into it into an exponential equation that we could then solve just thinking of powers of a. Okay, and we're going to see some examples of that down below. And the homework for class is actually just computing some simple cases of this function. All right, remember, keep in mind that the a is neither an input nor an output into this function. It's something that's fixed ahead of time to define what the function is. So I get a different function for every base a, right? And that would have a different graph and everything. Okay, now there's two super important conventions with logarithms that we're going to need to remember because they're going to come up all the time, right? So we have defined right now log base a, right? And that little a is a subscript. So first off, if you see a log and it doesn't have a subscript, okay, every logarithm has to have a base. When you don't see that base, then that base is automatically 10. Okay, so when I just write log by itself, what I mean is log base 10, and that's called the standard logarithm. Right, now why is base 10 a standard logarithm? Well, only because it happens to be an easy logarithm to estimate, right? And that's only because we live in a base 10 world, right? All of the numbers that we write are in base 10, so it makes it pretty easy to compute powers of 10, and conversely to compute log base 10 fairly easily. But mathematically, there's nothing very special about log base 10. And when it shows up, it tends to show up in things like engineering, sometimes in physics. Okay. It's actually much more common to see the second one. When you see ln, that means log base e. Okay. So instead of writing log base e, we're going to always write ln. And that's what's called the natural logarithm. So the ln actually stands for natural logarithm. The reason why we write it ln instead of nl is because it's actually Latin. I think it's like logarithm naturali or something like that. So that's why it's in that particular order. Okay, so make sure that's in your notes because we're gonna start using that notation right away. So let's do an example of computing a log. I want to compute log base 2 of 8. Okay, so to do that, I'm just going to use that definition, and I'm going to turn this into a problem with exponents. So first what I do is I give a name to the thing I'm trying to compute. So I give that name y, like for output, right? So I'm going to start with the equation log base 2 of 8 equals y, and I want to solve for y. So I'm going to turn that equation into an exponential equation. And you do have to remember how to do this. Remember that 2 is going to become the base of the exponent. The thing I'm solving for, the y, is actually the exponent. And then the 8 becomes the result. So now I'm trying to solve 2 to the y equals 8. And the only way to do that is by thinking of powers of 2 and realizing that 2 times 2 times 2 equals 8. So the only way I'm going to do this by hand is if I take a number that happens to be a nice power of my base, like a whole number. If it's not a whole number, then I'm going to need a calculator to solve it, and I'm going to show you how to do that in class. It's much easier to show you how to use your calculator in class than it is on a video. Okay, so what's the final answer to this problem? Log base 2 of 8 equals 3. Okay, so at this point, I'm going to show you the homework problems right now, the ones that I'd like you to bring into class. And if you'd like, you can pause the video right now and try them. In a second, I'm actually going to give you a couple hints if you're stuck. But I would say first try all of them that you think you can do. Okay, so a couple hints. One is that remember that these first 4 logs don't have bases. So remember that means that the base is 10. Okay, so that means that for the first 4 problems, you're trying to solve like 10 to the something equals this. So set it up like an exponential equation, like we did in the problem, or like we did in the example. Now you do enough of these, and I think it's good. It'd be good to think about how you might do it without setting up that separate equation, but that's kind of like a more advanced step. And when you're just starting out, turn it into an exponential equation and solve it that way. Okay, another hint for the last one. So first off, remember that ln means log base e, so e is the base of the log. And then I want you to think, well, first off, you don't have to expand out e to the 4, right? You could plug that into your calculator and find out what e to the 4th is. It's some number, but that's actually not going to help you. So just leave this e to the 4th alone and set up that exponential equation. And then if you do that correctly, the answer will be pretty obvious, I promise. Okay, so thank you. I'll see you in class. Best of luck.